Welcome back everyone. In this lecture we will continue to review some basics of representation theory. So, let me first recall what is a representation. So, let A be an associative algebra So, as I said before, we always assume that it has unity, which is a multiplicative identity. So, recall that a representation is a map from A to endomorphism of V. So, it is an algebra homomorphism. So, this is what we call a representation. Indeed, the pair V comma rho is called representation of A, but simply either we call rho as a representation or V as a representation. So, V is mostly called a representation space, but we can call it representation of A. So, now recall that this endomorphism of V actually has this associative algebra structure, and we demand this rho to actually reflect the algebraic structure that we have for A via this map rho. So, what is a subrepresentation? So, it is a subspace of V which is invariant under actions of these elements of capital A. So, recall subrepresentation. So, it is a subspace of V to begin with, such that whenever you apply rho of A on W, then we which actually map to W for all A in A. So, then we call this V as a subrepresentation. As I told before, you can actually define this induced map starting with rho. So, you can define this rho W from A to endomorphism of W by taking A goes to rho of A restricted to W, and one can easily check that if we assume that W is invariant under actions of all elements of capital A, then this induced map rho W is a representation of A. So, that means it is a algebra homomorphism from A to endomorphism of W. So, I will leave it to check this. So, now we will define this important terminology called irreducible representation. So, a representation is said to be irreducible or simple if the only subrepresentation of that representation are 0 and itself. So, let me just write it properly. So, irreducible or simple representations. So, we always assume that irreducibles are non-zero representations. So, we start with non-zero representations of A and we call it simple or irreducible if the only subrepresentations of A are 0 and itself. So, it is easy to see that the whole space and 0 space, both of them are subrepresentations. So, we are demanding that a representation is simple if they are the only subrepresentations of that representation that we started with. So, we will actually see later how these irreducible representations are going to play important role in representation theory of finite groups, but anyway it is something very simple to define. I have defined here. So, now let us define equivalence in representations. So, that means isomorphic copies. So, for that first let us actually define what is called homomorphism of representations. So, let us start with two representations, let us call them V rho 1 and then W rho 2. So, let us say these two are two given representations of capital A. So, that means we have these maps rho 1 from A to endomorphism of V and then rho 2 again from A to endomorphism of W. So, now given these two representation, we want to talk about homomorphisms between those two representations. So, it is a linear map pi from V to W such that it commutes with the action of all elements of A. So, more precisely, so it satisfies these two conditions. So, first of all, to begin with, pi is a linear map, and secondly, when you actually apply A on V and then apply pi, so pi of A V, that is supposed to be A pi V for all A in A and V in V. So, let us elaborate what does it mean by pi actually commutes with the action of capital A. So, let us rewrite everything in terms of the maps. So, we have the following diagram. So, let us draw it. So, you have this pi which is defined from V to W, and then we have this rho 1 which is a map from A to endomorphism of V, and then this rho 2 which is a map from A to endomorphism of W. So, now this pi is defined between V and W. So, given any element A in A, so we can talk about these two maps rho 1 of A and rho 2 of A. So, those maps actually act on the respective spaces V and W. So, now we can have a diagram like this. So, now if we actually translate the condition pi of A V as A pi of V. So, this means in terms of maps pi of rho 1 of A applied on V is supposed to be equal to rho 2 of A applied on pi of V. So, that means this diagram must commute. So, if you actually take the composition of these two maps, pi composed to rho 1, that is supposed to be equal to rho 2 pi composed of rho 1 of A supposed to be equal to rho 2 of A composed with pi. So, you chase the diagram from top to bottom like this or top to bottom like this, both ends up to be same maps. That is what the meaning of this diagram commute. So, if pi satisfies a linear map satisfies this condition, then we call this as a homomorphism of these representations of A. So, pi is because of this property, pi is actually sometimes called intertwining operator. So, that is the terminology some old books use. So, sometimes pi is called intertwining operators. Okay, so, if we have this homomorphism, then immediately one can consider this home space which is the set of all homomorphism of representations V and W of A. So, that the set of all homomorphisms of representations. So, this it is easy to check, this is indeed a subspace of the actual home space, which is the set of all linear maps from V to W. The home A V W is a C subspace of home V W. So, once we have the notion of homomorphism, then actually we can talk about the kernel image and the first isomorphism theorem. So, let me just state and prove the first isomorphism theorem. It is a very important theorem that we will be used frequently everywhere in representation theory. So, let us start with the homomorphism of representations of A, and then immediately one can consider the kernel and image. So, let me just write it what it is. So, let us fix this homomorphism of representations of A. So, then we can define what is called the kernel. So, the kernel is going to be those vectors which are annihilated by pi, and it is easy to see that. So, this is indeed a subrepresentation of V. So, it is a subrepresentation of V, and it is indeed one line check. So, let us take a vector from the kernel. So, then immediately what we have, pi of V is going to be 0. So, now if we take some element A from capital A, then if we compute pi of A V, since the action of A and pi commutes, so we get this is equal to A pi V. So, that means this is equal to 0. So, this implies that A V is again inside the kernel of pi, and indeed the same equation tells you that the image of pi is also a subrepresentation of W. So, the image of pi, so it's consisting of all the images of elements of capital V. So, this is also a subrepresentation of W. So, this is again follows from the same equation, pi of A V is nothing but A pi of V. So, that implies pi of A V is again elements of image pi for all A in A. So, that means image pi is invariant under the action of capital A. So, in order to state the first isomorphism theorem, we need to define the quotients. So, quotients are defined in an obvious way. So, the quotient, so you take a subrepresentation of V, so where V is a representation of capital A. So, then we can actually consider this quotient space, which is V modulo W. So, this is the quotient space. So, this consisting of all cosets corresponding to W. So, then we can actually define an action of capital A on this V modulo W. So, that makes this V modulo W as representation of capital V. So, let us fix this notation rho as a representation of capital V. So, that means it is a map from A to endomorphism of V. So, now since W is indeed subrepresentation of capital V, so for any A in A, if we take rho A of W, so that is going to be subset of W. So, that means this rho A induces a map on the quotient. V modulo W to V modulo W. So, that is given by you take a coset V plus W and then send it to rho A V plus W. So, this defines a well defined linear operator on V modulo W. So, let us call this as V mod W, rho of A V mod W. So, then it is clear that that is actually going to give you the necessary action that we are interested in. So, now we define this rho V modulo W, which is a map from A to the endomorphism of V modulo W. So, that is given by A is mapped to this rho A of V modulo W, which is given by this formula. And it is easy to check, this defines algebra homomorphism from capital A to endomorphism of V modulo W, and because of that we get a representation of capital A. So, that is called quotient representation. So, we leave it to you to check this defines indeed a representation. So, now here we state the first isomorphism theorem. And I will give proof of only this theorem. All other remaining isomorphism theorems are immediately follow from the arguments that you have seen in linear algebra. The only thing that we check, the whatever the maps that we are going to define, they are all like now homomorphism in the world of representations. Okay, so, what the first isomorphism theorem says? So, we start with the representation V. So, let us say V comma rho is the representation of capital A, and W is a sub representation of capital V. So, then immediately we see that we can actually talk about the quotient of V given by V modulo kernel of pi. So, if we have, so let us fix this map, sorry. Okay, I want to write in terms of the maps. So, let us take V comma rho to be representation and W comma rho dash to be another representation of A, and pi is actually a homomorphism of representations. Okay. So, then we can actually form these spaces. So, V modulo the kernel and we have the image. So, then pi naturally induces a map from V modulo the kernel to the image. So, that is indeed an isomorphism of representations. So, that is what first isomorphism theorem guarantees. So, the map pi tilde is induced from pi, which is given by you take the coset corresponding to any element V, then that is mapped to just pi of V. So, that is how the map pi tilde is defined. So, pi tilde of V plus kernel pi is exactly pi of V. So, this is indeed an isomorphism of representations of V. So, what does it mean by isomorphism? So, we need to check only that this is indeed commutes with the action of capital A. We already know that this is going to be vector space isomorphism. So, now we need to actually check it is isomorphism of representations. So, let us check that. So, the only thing that is supposed to be checked when you apply pi tilde on this A V plus kernel pi. So, then we should get A of pi tilde of V plus kernel pi. Okay. All the respective maps that are involved here, they are all well defined, there is no issue. So, now to check this, we need to just see how all these things are defined. So, A of V plus kernel pi. So, this is indeed induced from the original representation. So, this is going to be, so maybe let me write it in terms of the maps. So, I guess I fixed rho and rho dash. So, this is going to be rho of A applied on this. So, then this is exactly rho of A V plus kernel pi, and now if we apply pi tilde, then pi tilde of rho of A V plus kernel pi is going to be exactly pi tilde applied on rho of A V plus kernel pi. But by the definition of pi tilde, so V plus kernel pi map to pi of V. So, because of that we can easily say this is mapped to pi of rho of A V. But pi and rho commutes. So, then you get rho dash of A pi of V. So, because pi composition rho of A is same as rho dash A composition pi, as pi is a homomorphism of representation. So, but by the definition of pi of V, we can see that that is same as this pi tilde of V plus kernel pi. So, this is going to be exactly equal to rho dash of A applied on pi tilde of V plus kernel pi. So, this tells that the induced map indeed homomorphism in this representation world. So, already we know that this is going to define isomorphism of vector spaces, and since this is indeed homomorphism of representation. So, that tells us that this is indeed an isomorphism of representations of A. Okay. So, now like other isomorphism theorems will follow immediately from the first isomorphism theorem. So, I am going to just state it and then I will leave it to you to check these statements. So, here is the exercise. Suppose if we start with two subrepresentations of V, then using them we can actually form some other representation by taking sums and intersections. So, let us actually take two subrepresentations of V. So, then one can prove that the sum, so which is defined to be W1 plus W2, where W1 comes from capital W1 and W2 comes from capital W2. So, this is indeed a subrepresentation of capital V. So, I am going to use this notation less than or equal to instead of containment in order to emphasize. So, these are all subrepresentations of capital V, subrepresentation of capital V. So, now we can also talk about the intersections. So, if we take intersection of W1 and W2, so that is also a subrepresentation of V. Indeed, one can generalize this further. So, any arbitrary intersection of subrepresentation is going to be subrepresentation. So, more generally, any subrepresentation, sorry, intersection of collection of subrepresentations is again subrepresentation of V. That means you take any W alpha which is subrepresentation of V indexed over some indexing set capital lambda, then you take the intersection of all this W lambda or W alpha. So, this is again subrepresentation of capital V. So, now we state the second isomorphism theorem. So, which actually tells about the quotient of W 1 plus W 2 over W 2 and W 1 over W 1 intersection W 2. So, we know from linear algebra that if we take the quotient of W 1 plus W 2 mod W 2, so that is going to be isomorphic to as a vector space W 1 mod W 1 intersection W 2. But this is also true as representations of capital A. So, note that all the respective spaces considered here, they are all subrepresentations of capital A. So, the quotients are also representations of A. Okay. So, now let me state the next isomorphism theorem. So, order of this isomorphism theorem might change depending upon the book. Anyway, these are all the important isomorphism theorems. So, again we fix a representation of capital A. Now, we will actually consider two subrepresentations. So, let U and W be two subrepresentations of capital V, where U is contained in W, W is contained in V. So, these are all subrepresentations of capital V. So, now what we can do, we can actually make these quotients V mod U and then W mod U. And we already know from linear algebra there is a natural inclusion of W mod U inside V mod U, which is just comes from the inclusion of W inside U inside V. So, now we can prove that this W mod U is indeed a subrepresentation of V mod U. So, the quotient is indeed subrepresentation of V mod U. So, now we can actually take the further quotient V mod U modulo W mod U, and from linear algebra we know that this is supposed to be isomorphic to the quotient V modulo W as vector spaces. And it is not that hard to check, this is also isomorphism as representations of V. So, this is also an isomorphism as representations of V. So, here is another exercise actually which actually talks about the subrepresentations of V mod U. So, if you think about it, actually every subrepresentation of V mod U, it is of the form W mod U for some W that contains U. So, indeed, so that is actually encoded in the lattice theorem. So, here is the lattice isomorphism theorem. So, let us actually consider this natural quotient map from V to V modulo W. Let us say W is a subrepresentation of V and pi is the quotient map. So, pi is given by pi of V goes to V plus W. So, V map to the respective coset, and it is easy to check this is a homomorphism of representation. So, now under this quotient map we know that subspaces of V that contains W will correspond to subspaces of V modulo W, and that correspondence actually respects representations as well. So, what I mean by that? So, you can start with the set of all sub representations of V containing W. So, from this set we can actually have one-to-one correspondence to sub-representations of V modulo W, the set of all sub-representations of V modulo W, and we have this one-to-one correspondence, where the correspondence is given by you take any U containing W, which is a sub-representation. So, then you just map that U to U modulo W. So, that is the map, and for the inverse, so if you start with any U here, then we know that, so any sub representation must be of the form some representation containing W. Okay. So, maybe let me write it like this. So, if we start with some U dash here, then we can easily prove that. So, by taking the pi inverse of U dash, so that is going to be the role of U, which will definitely contain W. So, then this U dash is going to be naturally equal to U modulo W. This is the correspondence given by these maps, and this correspondence is not just correspondence of representation, they also kind of obeys sums and intersections. It is indeed a lattice isomorphism. So, what I mean by obeys? So, this correspondence commutes with the process of taking sums and intersections. So, that is the advantage of this lattice correspondence, and this lattice correspondence is very important in representation theory. We have already seen the importance of this isomorphism theorems in group theory, ring theory and so on. So, we will also continue to use these isomorphisms in representation theory. Okay. So, now we will introduce the direct sum. I already partially introduced, but anyway let me recall what is the direct sum. So, again let us start with two representations V comma rho 1 and V comma W comma rho 2. So, these are the representations of capital A. So, then V direct sum W is nothing but you take direct sum of individual vectors. So, sometimes you can identify that with the pair V comma W, but let me use this V direct sum W as a notation. So, V in V and W in W. So, now the direct sum of these two representation is defined to be taking the respective direct sum of the maps rho 1 A and rho 2 of A. So, note that rho 1 of A is a map from V to V and rho 2 of A is a map from W to W, and this rho 1 of A direct sum rho 2 of A, it is a map from V direct sum W to V direct sum W. For example, in terms of the basis, you can see that if you put together basis of V and W, so then let us say B1 is basis of V and then B2 is basis of W, then the basis B, which is obtained by combining B1 and B2. So, then the matrix of this operator rho 1 direct sum rho 2 of A, it looks like you take rho 1 of A and then with respect to B1 0 0 here and then rho 2 of A with respect to B2 here. So, it is basically a direct sum of these respective matrices. Okay, I will stop here and I will continue with reviewing basic representation theory in the next class. Thank you.